Radar cross-section is a measure of how detectable an object is with a radar. A larger RCS indicates that an object is more easily detected. An object reflects a limited amount of radar energy. A number of different factors determine how much electromagnetic energy returns to the source, such as material of which the target is made, absolute size of the target, relative size of the target, the incident angle, reflected angle, the polarization of transmitted and the received radiation in respect to the orientation of the target. While important in detecting targets, strength of emitter and distance are not factors that affect the calculation of an RCS because the RCS is a property of the target reflectivity. Radar cross-section is used to detect planes in a wide variation of ranges. For example, a stealth aircraft will have design features that give it a low RCS, as opposed to a passenger airliner that will have a high RCS. RCS is integral to the development of radar stealth technology, particularly in applications involving aircraft and ballistic missiles. RCS data for current military aircraft is most highly classified. In some cases, it is of interest to look at an area on the ground that includes many objects. In those situations, it is useful to use a related quantity called the differential scattering coefficient I0 florins, which is the average radar cross-section of the set of objects per unit area. Where RCSI is the radar cross-section of a particular object, and I is the area on the ground associated with that object. Definition: informally, the RCS of an object is the cross-sectional area of a perfectly reflecting sphere that would produce the same strength reflection as would the object in question. Thus, RCS is an abstraction. The radar cross-sectional area of an object does not necessarily bear a direct relationship with the physical cross-sectional area of that object but depends upon other factors. Somewhat less informally, the RCS of a radar target is an effective area that intercepts the transmitted radar power and then scatters that power isotropically back to the radar receiver. More precisely, the RCS of a radar target is the hypothetical area required to intercept the transmitted power density at the target such that if the total intercepted power were re-radiated isotropically, the power density actually observed at the receiver is produced. This is a complex statement that can be understood by examining the monostatic radar equation one term at a time. Where equals power transmitted by the radar, equals gain of the radar transmit antenna, equals distance from the radar to the target, equals radar cross-section of the target, equals effective area of the radar receiving antenna, equals power received back from the target by the radar. The term in the radar equation represents the power density that the radar transmitter produces at the target. This power density is intercepted by the target with radar cross-section, which has units of area. Thus, the product is the dimensions of power, and represents a hypothetical total power intercepted by the radar target. The second term represents isotropic spreading of this intercepted power from the target back to the radar receiver. Thus, the product represents the reflected power density at the radar receiver. The receiver antenna then collects this power density with effective area, yielding the power received by the radar as given by the radar equation above. The scattering of incident radar power by a radar target is never isotropic, and the RCS is a hypothetical area. In this light, RCS can be viewed simply as a correction factor that makes the radar equation work out right for the experimentally observed ratio of. However, RCS is an extremely valuable concept because it is a property of the target alone and may be measured or calculated. Thus, RCS allows the performance of a radar system with a given target to be analyzed independent of the radar and engagement parameters. In general, RCS is a strong function of the orientation of the radar and target, or, for the bistatic, a function of the transmitter target and receiver target orientations. A target's RCS depends on its size, reflectivity of his surface, and the directivity of the radar reflection caused by the target's geometric shape. Factors that affect RCS. Size equals, as a rule, the larger an object, the stronger its radar reflection and thus the greater its RCS. Also, radar of one band may not even detect certain size objects. for example. 10 centimeters can detect raindrops but not clouds whose droplets are too small. Materials such as metal are strongly radar reflective and tend to produce strong signals. Wood and cloth or plastic and fiberglass are less reflective or indeed transparent to radar, making them suitable for radomes. Even a very thin layer of metal can make an object strongly radar reflective. Chaff is often made from metallized plastic or glass with microscopically thin layers of metal. Also, some devices are designed to be radar active, such as radar antennas, and this will increase RCS. Radar absorbent paint. The SR-71 Blackbird and other planes were painted with a special iron ball paint. This consisted of small metallic coated balls. Radar energy is converted to heat rather than being reflected. Shape, directivity and orientation. The surfaces of the F-117A are designed to be flat and very angled. This has the effect that radar will be incident at a large angle that will then bounce off at a similarly high reflected angle. It is forward scattered. The edges are sharp to prevent there being rounded surfaces. Rounded surfaces will often have some portion of the surface normal to the radar source. As any ray incident along the normal will reflect back along the normal, this will make for a strong reflected signal. From the side, a fighter plane will present a much larger area than the same plane when viewed from the front. All other factors being equal, the plane will have a stronger signal from the side than from the front, so the orientation between the radar station and the target is important. Smooth surfaces. The relief of a surface could contain indentations that act as corner reflectors, which would increase RCS from many orientations. This could arise from open bomb bays, engine intakes, ordnance pylons, joints between constructed sections, etc. Also, it can be impractical to coat these surfaces with radar-absorbent materials. Measurement. The size of a target's image on radar is measured by the radar cross-section or RCS, often represented by the symbol I-florin and expressed in square meters. This does not equal geometric area. A perfectly conducting sphere of projected cross-sectional area 1m2 will have an RCS of 1m2. Note that for radar wavelengths much less than the diameter of the sphere, RCS is independent of frequency. Conversely, a square flat plate of area 1m2 will have an RCS of I-florin equals 4 I2 Australian Euros/I2, or 13,982 m2 at 10 GHz if the radar is perpendicular to the flat surface. At off-normal incident angles, energy is reflected away from the receiver, reducing the RCS. Modern stealth aircraft are said to have an RCS comparable with small birds or large insects, though this varies widely depending on aircraft and radar. If the RCS was directly related to the target's cross-sectional area, the only way to reduce it would be to make the physical profile smaller. Rather, by reflecting much of the radiation away or by absorbing it, the target achieves a smaller radar cross-section. Measurement of a target's RCS is performed at a radar reflectivity range or scattering range. The first type of range is an outdoor range where the target is positioned on a specially shaped low RCS pylon some distance downrange from the transmitters. Such a range eliminates the need for placing radar absorbers behind the target, however multi-path interactions with the ground must be mitigated. An anechoic chamber is also commonly used. In such a room, the target is placed on a rotating pillar in the center, and the walls, floors and ceiling are covered by stacks of radar-absorbing material. These absorbers prevent corruption of the measurement due to reflections. A compact range is an anechoic chamber with a reflector to simulate far-field conditions. Typical values for a centimeter wave radar are: insect 0.00001 mass squared, bird 0.01 mass squared, stealth aircraft